Well, hi guys. What we're going to have a look at here in this little video is a little bit of a revision work around the idea of using indices, and we'll also have a little bit of a look at a bit of work on expanding, which should be a little bit more straightforward. Okay, but indices or powers, these are something which you've used a lot over the last few years in maths. So for example, if you had 2 to the power 3, okay, and we wanted, for example, to maybe multiply that with 2 to the power 4, okay, then using some of these indice rules, hopefully you might realize, well, that's 2 to the power 7. So these rules for indices, sometimes called the laws of indices, okay, what we're going to have a brief look at here is what they are, a little bit of background as to where they come from, and a few examples of how to use them. So these laws of indices, okay, what do they say? Well, okay, we're just going to list them here. Okay, this one, a to the power of m times a to the power of n, apparently is equal to a to the power of m plus n. Okay, and number 2, when we're dividing a to the power of m over a to the power of n, okay, then we can simplify that, apparently, with a to the power of m minus n. Now I'm saying apparently because I never like to sort of just accept rules of maths. Okay, rules of maths are generalizations that can be proven. So for a number of these things, we'll have a look at some justification of them. Okay, so why are these things true? And I hope you've asked those questions yourself in class before, rather than just accept, okay, well, if we've got something presented like this one to you, have you asked, well, how do I know that this is true? And this fourth rule, a to the power of n times b to the power of n is equal to a times b to the power of n. Once again, apparently. And we'll finish it off with this one, a to the power of negative m equals 1 over a to the power of m. Okay, and a little aside there, that a cannot equal 0. Okay, now it would take a while to go through a complete proof of all of these, so I'm just going to take a look at a couple of them, maybe 3 of them at this stage, and we might explore the other 2 or 3 that we don't have a look at the video here in class time. But let's have a look at this number 1. Okay, so now, this is a generalization, this rule, of what you do with powers. Now, in powers, let me just use a couple of bits of terminology here. Okay, this a is called the base. So if we had a numeric example, 7 to the power of 4, 7 is called the base. And m is called the indice, or the power, or sometimes the exponent. So here, this 4 is the indice. Okay, what this is saying then is that if you've got something like, and let's take a numeric example to begin with, 7 to the power of 4, and we're multiplying it, say, with 7 to the power of 5. Now, notice in this rule up here that a is mentioned twice here, so it has to be the same base. And what this is simply saying is, well, we've got 7 multiplied together 4 times. Okay, in fact, I'll put that equals underneath. And then we're multiplying, that dot means multiply in maths, in algebra especially, with another 7, or 7 being multiplied together another 5 times. Well, if you look at that, that simply means we've got 7 being multiplied together 9 times in this case. And of course, 4 plus 5 would give that 9 as well. And that's exactly what that is meaning. This is 4 sevens being multiplied together and another 5. So how many altogether? Well, 9 times you're multiplying 7 together, so 7 to the power of 9. And that's true for really any situation then where you've got that same base. Okay, so if we had x to the power of 12 times x to the power of 72, well, I definitely don't want to have to write that out, but let's just think this through. X multiplied together 12 times, x multiplied together 72 times, and we're multiplying that. Well, that means that we're multiplying x together a total of 84 times, 12 and another 72. So that should be x to the power of 84 then. So yes, we can add those two powers then in that situation. Okay, so that's the sort of justification of where this rule is coming from. In a very similar way, let's have a look at number 2. Okay, number 2, let's once again have a look at a numeric example of this. Oops, that should be an N, not an M. Let's just rub that out and start that again. Okay, so we've once again got the same base here. That's really important, as we'll see in a minute. So trying to justify this with another numeric example, let's say 8 to the power of 7 over 8 to the power of 4. Well, according to that, it should be 8 to the power of 3. Well, why? Why is it okay to simply subtract those two indices? Well, the idea is here that you are working with common factors. 2 more to go there. So 8 being multiplied together 7 times, and we've got, that was a mistake again. Let me just try and erase that carefully without erasing everything. We're multiplying on the bottom 8 being multiplied together 4 times. Now I'm deliberately just showing there, okay, that those 4 8s there, what about the times in between? Well, we can put that, but that means the same as this. 8 divided by 8 times 8 divided by 8 times another 8 divided by 8. I know this is a little tedious, but bear with me. And then we've got these 3 8s being multiplied together left over. Now what we've got here is we've got the same number divided by itself. So that's a common factor. So we can simply say, well, that simplifies down to 1. Excuse the phone there, guys. I'm simply going to ignore it. Okay, and so we're left with, well, what are we left with? 3 8s being multiplied together times a whole lot of 1s. Well, that's just 3 8s being multiplied together, so 8 to the power of 3. So, yeah, we could have got that same result, of course, a lot more quickly by simply subtracting the top power minus the bottom one, giving that 8 to the power of 3. What do you do if the top power is smaller than the bottom power? Well, not a problem. Okay, we're going to have 5 to the power of, let's say, 4 over 5 to the power of, let's make that 12. 12? No, too big. Not if I'm going to write it out by hand. That's just going to take too long. Let's make that a little smaller. Let's say 5 to the power of 8. Okay, so what does this mean? Well, this means 5 getting multiplied together 4 times on top over 5 being multiplied together 8 times. Sorry guys, let me get rid of that. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what's happening here? Well, the same thing is up here. We've got 5 being divided by itself, and that's happening 4 times. So what are we left with? Well, we're left with a whole lot of 1s being multiplied together on top. That's 1. And we've got 1 being multiplied together, which just gives 1. That happens 4 times, so still 1 though up to that point. Then 4 5's being multiplied together, which I can write as 5 to the power of 4. Okay, you may think, well, that doesn't work because you need to subtract the top power minus the bottom one. 4 minus 8, that's 5 to the power of negative 4. And that's absolutely true. So that helps to bring us basically to this rule number 5 here. And I'll just make a little bit of room down the bottom here in the middle where I've got some room here. That 5 to the power of negative 4, does that mean the same as 1 over 5 to the power of 4? Yes, it does. And the simplest way to confirm that is to plug that into your calculator and plug that into your calculator and show that they are equal. Okay, and so that helps to actually show that if you have a negative power, a negative indice, that is same as 1 over a to the power of that positive indice. Okay, so there's a couple of those indice rules, and then we brought in this number 5 here as well. I haven't talked about 3 and 4. Let's have a look at that in class. But yeah, there's a couple of the basic rules of indices, in fact 3 of them, which I hope gives some sort of background to. Now, what about some examples then? Well, let's have a look. Okay, let's go to a new page here, and yeah, we can have a look at plenty of simple examples, and I don't want to bore you with some of these, but if we had something like a to the power of 12 over a to the power of 5, you know, that simplifies to a to the power of 12 minus 5, which is a to the power of 7. But that's the sort of work you would have done back in year 10 and 11. Okay, let's have a look at something which is much more level 3 stuff. Okay, so let's say we had something like 2 to the power of n plus 2 being multiplied with 6 to the power of n minus 4 all over 12 to the power of n minus 1. Now that's a different kettle of fish, isn't it? And you're asked to simplify. Wow, would you believe that simplifies to 1/27th? Well, maybe not, but let's have a look and see how it does. Okay, if I'm going to try and simplify this, well, I can only apply those rules of indices if I have the same base. Okay, so that 2, well, 2 is a prime number. I can't really rewrite 2 as anything else apart from 2. But 6, that's a different story. I could rewrite that as 2 times 3. So 2 times 3 all to the power of n minus 4. Now that actually means we're going to have to bring in one of those other rules of indices we didn't talk about in a moment, a little bit previously I mean, but we'll have a look at that then. And what about 12? Okay, sorry guys, I'm just going to ignore that phone yet again. Okay, well, I'd like to have 12 written as some sort of multiple of 2 and 3 because I'm using 2 and 3 up here. So if I look at 12 and do a little bit of a factor tree, so 2 times 6 here, but 6 can be split into 2 times 3. This is known as a prime factor tree. If you look at the ends of the branches here, that means that 12 can be written as 2 times 2 times 3. 4 times 3, that's 12, yeah. So in other words, 2 to the power of 2 times 3. Okay, so does that mean I could rewrite this as 2 squared times 3 all to the power of n minus 1? Yes, it does. Okay, so what can I do with that? Well, one of the other rules of indices that we didn't take a look at a little while ago was what happens if we have something like a to the power of n times a to the power of hold on, let me just go back a page here. What was that one? Oh, sorry. We had b to the power of n. Okay, well, is that the same as a times b to the power of n? Well, yes it is. If we have a look, say another numeric example, so we had 2 to the power 2 times 7 to the power of 3. What does that mean? Well, that actually will give 2 to the power of 3 times 7 to the power of 3. And once again, you could prove this by actually plugging both sides into your calculator. So if we had, this is basically 14 to the power of 3, is that equal to, that's going to be 8 and 7 to the power of 3, whatever that is, but it's going to give the same result. So yeah, this here is another one of those things which is true and can be demonstrated with some numeric examples here. I know that's not strictly an algebraic proof, but it's a justification. So how would we use something like that, perhaps in reverse here on this side? Well, 2 to the power of n plus 2, let's leave that alone. But this can be written then as 2 to the power of n minus 4 times 3 to the power of n minus 4. Okay, that's splitting this up by taking this kind of statement and working it in reverse. So each of these to the power of n, 2 then to the power of n minus 4, 3 to the power of n minus 4. Okay, what about the bottom line? Well, that's 2 squared to the power of n minus 1. And I'm not going to put that as a 4, deliberately want to leave it as a 2 power. And that is also 3 to the power of n minus 1. Okay, let's keep going. What about this now? Can we simplify this? And can we simplify these two things here? Well, let's actually deal with that top line. Remember that rule we looked at on the previous page? Same base, different powers. We can add those powers. Well, it's the same base here, different powers. We can add those two. So n plus 2 plus n minus 4. That's a little bit of algebra there for you. Well, that looks to me like 2n minus 2. Gathering like terms. Okay, so 2n minus 2. There's n and another n, so 2 n's. 2 take away 4, that's the minus 2. Alright, that top, rest of that, just leave it. Now what about this thing here? Well, a to the power of something all raised to a new power. Okay, let's take a look at another numeric example. 3 to the power of 4, let's say to the power of 3. Well, that means 3 to the power of 4 being cubed. So in other words, 3 to the power of 4 being multiplied together 3 times. Well, if you use that law of indices up here, this one again, that would be 3 to the power of 12. Add those 3 4s together. Okay, could we have got there much more quickly? Yeah, we could have. We could have multiplied those two together. And that's going to give 3 to the power of 12 as well. So, same result. So that means that we can get this simplified much more quickly by multiplying those two powers together. Okay, so let's do that on the bottom line here. This will become 2 to the power of 2n, 2 times n, 2 times negative 1, 2 to the power of 2n minus 2 times, and the rest of the bottom line, 3 to the power of n minus 1. Okay, can we go any further? Well, yes, we can. Notice that we have the same power of 2 here. So that power of 2 divided by itself. Well, that divided by itself should be 1. And now what we've got is a situation where we've got 3 to the power of n minus 4 over 3 to the power of n minus 1. Okay, and let's remind ourselves of what we do there. We can subtract those powers. So let's do that. 3 to the power of n minus 4 minus the bottom line. Okay, what's that going to give? 3 to the power of n minus 4 minus n plus 1. Okay, what does that simplify to? or n take away n 0, negative 4 plus 1 is negative 3. Oh, there we go. So it does simplify to the 3rd power of negative 3. But Mr. Swanwick said it was 1/27th before. So where did that come from? Okay, well, once again, we can rewrite those negative powers. Let's remind ourselves of that. A to the power of negative m is the same as 1 over a to the power of m. So it's 1 over 3 cubed. And 3 cubed is 27. So it's 1 over 27. Okay, ta-da! Right, that was a bit of a mission, wasn't it? But it really revised, I think, and applied all these different rules of indices in one question. So I think that was a pretty, dense and intense sort of question, but it did revise a lot of those basic concepts in a sort of pretty challenging way. Okay, guys, I think we might just have a look at one last example, and then I'm going to get you to try a couple yourself. Alright, let's take something a little simpler. I do mean a little simpler, it's not that simple. Right, let's take this one. Let's say we're told if 5 to the power of m is equal to 4, simplify 5 to the power of 1 minus 2m. Okay, well, how am I going to use that? I have to somehow rewrite this where I've got 5 to the power of m on its own. How can I do that? Well, I do know that if I've got a to the power of m times a to the power of n, it means I add those two. So can I do that in reverse? Yeah, I think so. So maybe 5 to the power of 1 times 5 to the power of negative 2m. Okay, well that's pretty good, because that means that 5 is just a 5, and that a to the power of m to the power of n is a to the power of m times n. Okay, maybe I could rewrite this then as 5 to the power of m to the power of negative 2. So if I multiply those two, it gives me that back, so I'm just working that in reverse again. Well, this is looking pretty good, because now I've got 5 to the power of m, and we're told that's 4. So if that's true, well, this means I've got 5 times 4 to the power of negative 2. And let's not grab the calculator. Let's remember that something to a negative power is 1 over a to the power of that positive power. That means I can rewrite that as 1 over 4 squared. And that's just 5 over 16 then. So there we go. There's another one that simplifies to a numeric result. Okay, now don't expect that always to happen, that you get a numeric answer, but sometimes you do. Alright, so I'm going to throw in a couple of questions here after I've finished speaking. So have a go at those, and we'll catch you in class soon. Okay, see ya.